All right.
He's the guy who just walked away.
We're recording.
Okay. So welcome to problem solving session number 1. Starting first, I'll just give a brief intro about how to install MATLAB. I guess all of you have done, but just to make sure that everyone's on the same page. This is the link that I had sent, and it has all the details. So you go to the Students tab, and then in the Students tab, it has all the instructions. Be careful with the activation ID. Don't forget to do that. And you need to enter the activation ID twice while creating your account and while installing. So it's pretty easy. Just follow the steps. Okay. Once this is done, your MATLAB window will look like this. Okay. So just a brief intro of what the MATLAB window has. On the left over here, so you can configure this orientation your ways, any ways you want. On the left over here, you have current folder, which is your current directory. So you can change this directory. Mine is current, the default directory of MATLAB. You can change this at any point of time. So you can save your files and functions in different directories. You have to go to the directory to actually run those scripts. Okay. The workspace actually shows you the variables. So if I just put a variable x equals to 3, so it shows you the variables and the matrices and everything. Okay. This is your command window. You can work directly in the command window. You'll see your outputs one by one after each command. If you want to write a program, like you write in C or C++, you go to New and you write a script. This can write your script. I'll just show you a script that I've already written. So this is like a different directory that I've made for this course. That's a different directory. So it will always ask you to change if I want to run this, it will ask me to change my folder, because currently it's MATLAB and I'm working in another directory. So we'll change the folder and run the things. Okay.
I'm sorry, how did you do that graph again?
Oh, I'm coming there. I'm coming there. This is just to show that how a script is run.
Okay.
Okay. So you can have your other things as well. So just a brief intro on what MATLAB is able to do. Okay. So first thing, if you see here, x is equals to 1, 2, 3, 4, 5. That's your row vector. So you have one row. This is one row, 5 columns. Okay. So you call it a row vector. Whereas a column vector, if you see the difference in the definition of these, a column vector has these semicolons. Okay. So a column vector will have 5 rows and 1 column. Alright. So that's basic row vector and column vector. Now the transpose of a matrix is it interchanges the rows and columns. So if you take the transpose of a row vector, any ideas of what you'll get? Yeah, you'll get a column vector. So this is your column vector. Okay? So transpose only interchanges your rows to columns and columns to rows. It's just a mirror image. Okay? Now, next thing, these are some functions which can generate matrices. So matrices have multiple rows and columns, like a 2 by 2 matrix, 2 by 3 matrix, where 2 by 3 means rows by columns. Okay? So just to make it concrete, if you have a matrix, a row vector, I have a horrible handwriting, so be fair with it. We'll have a 1 row and n columns. Okay? A column vector will have n rows and 1 column. Okay? And a matrix will be n by m. N rows, m columns. Okay? Wonderful. Okay, so transpose. So for transpose, if you want to take a transpose of a matrix in MATLAB, So if X is your matrix 1, 2, 3, 4, 5, then your transpose of X, Z, is X and an apostrophe. Okay? So your Z will be 1, 2, 3, 4, and 5. It will be a column vector. Okay? Another thing, if after each of these commands you don't put a semicolon, you'll see the output in the command window. And if you put a semicolon, you won't see an output in this command window. Okay, so a simple thing is, if I write A is equals to 2, I see the output in the command window. 1 second, sorry. This is weird. A is equals to 2, I see the output in the command window. If I write B is equals to 3 and I put a semicolon, I don't see an output, but B is equals to 3 is assigned in the workspace, if you can see. If my mouse moves, B is equals to 3. Okay. So semicolon is to repress the output in your command window, and it's a good idea. You don't want to see all the outputs while you're generating your code. Okay, but it's good if you don't use a semicolon to debug it. So be careful when you want to use a semicolon, when you don't want to use a semicolon. Okay, now to write inbuilt functions. So these are different. First of all, Magic gives you a square matrix always. So let me show it to you. Magic gives you a square matrix. The sum along the columns and sum along the rows and the major diagonals will be the same. That's what Magic is. Okay?
We can see that again.
So it will give you a square matrix. Square matrix means the number of rows and number of columns are same. So 3 rows and 3 columns in this case. The sum along the rows and sum along the columns of all the elements is the same. And along the diagonals as well. So that's why it's called a Magic matrix. Okay, it's just funky stuff that you can do. Ones. So for ones, you can generate a matrix with all element being 1. Okay? So here it is 4 rows and 2 columns. Okay? Similarly, if you want to have all the elements to be zeros, you have a zeros command. Here you have 2 rows and 3 columns. Okay. Now, I matrix. I gives you the identity matrix that you use a lot in your matrix theory. Okay. So only along the major diagonal the elements are 1 and everything else is 0. So this again gives you a square matrix. Whereas in ones and zeros you can have different number of rows and columns. In Magic and I you have same number of rows and columns. Okay. Now, how to, in MATLAB, yeah.
Those functions you created yourself or come with MATLAB?
These are inbuilt. They come with MATLAB. So Magic's ones, zeros, I, they're inbuilt. You can do them yourself as well. Just don't name them the same thing. Otherwise MATLAB will have a conflict. Okay? And it will overwrite the definition that it already has. So whenever if you're writing a function, give it a different name. Sort of write your own name in it or something. Okay? So in MATLAB you can have your own functions as well. So just as you can write a script, you can write a function. Okay? So in new you go to functions. Okay? This gives you a template of how to write a function. Let me open the one that I've already written to compare it with. So if you see the template, you have the function keyword, your output argument. Untitled means that's your function name. That's where you put your name over here. Input arguments are the parameters that you're passing. Okay? And this is your function body, and in the end you put an end. Okay? Now, just to give an example of how this is done, here I have the function keyword. AVG average is my output. Average of data is the function name. And X, Y are my inputs. Okay? And this is just taking the average of the two. Okay? Now, if I go back, the X, 2 that I have over here, the inputs, they can be scalar values like 1 or 2, 3, 4, whatever. Or they can be matrices as well. But be sure if you're doing matrices, they should be of the same size. Why? Because I'm directly adding these two here. If they're of different sizes, MATLAB will give you an error. Okay? So let's go here. My first matrix M, let me show you what M looks like. So M is 2 by 2 matrix, 1, 2, 3, 4. Just if you look at the definition of how I have defined M, my row elements are separated by space, and to go to the next column, I use a semicolon. Okay. N is another matrix that I've defined, 5, 6, 7, 8. And if I display AVG, it's the average of the two. So if you want to go further and calculate, average of 1 and 5 is 3, I believe. Yeah, it's 3. Average of 2 and 6 is 4. So it will take element-wise average. First element of M with first element of N, second element of M with second element of N, third element of M with third element of N, and so on. Element-wise. That's why you need it to be the same size. Okay. You can also do matrix multiplications in here. So if I do M into N, that's what. So just to give you a brief review of what matrix multiplication is, if I have a matrix P of size A by B, and if I have a matrix Q of size B by C. Oh, sorry. That's okay. So for the matrix multiplication, a direct matrix multiplication, these two inner dimensions, B and B, which I've shown the same, these should be the same. The inner dimensions have to be the same. So it has to be 2 by 3 and 3 by 2, or 1 by 4 and 4 by 1. Okay? It can't be 2 by 4 and 3 by 2. It will give you an error. Okay, so this will give you an error, and these two are fine. Okay? So that's how matrix multiplication works. The inner dimension should be the same. Now, if you already have a matrix, how will you check its dimensions? So are you done with the document? Let me go to the laptop. This is funky stuff. Okay, so I already have a matrix. Let's just imagine that we don't know what M is. Here we know, just imagine we don't know what it is. Let me see what the size of M is. So you have a command called size. I will give you the size. First it will give you the number of rows, second it will give you the number of columns. Okay? Now, if you remember, B was a matrix of 4 by 2. If I check the size of B, oh, actually, interesting. Size of B, 4 by 2. So number of rows and number of columns. You can take the size along one dimension. So if you only need number of rows, you don't want number of columns. It's like if you're running a loop based on the number of rows in a matrix. So you can do that with B, 1. It will take your size of the matrix only along the first dimension, that is the rows. Okay? Along the columns will be B, 2. So 1 is rows, 2 is the second dimension, the columns. Okay? Any doubts on anything? No? Okay, so the MATLAB that you have, it has a number of toolboxes, and just to see the toolboxes that you have in your MATLAB, you can do a simple command called VER. That's your version command. So it will give you the version details of everything that you have. So here, let me just pull this up. These are all the different kinds of toolboxes that you're working with. Okay? So communication systems toolboxes, it has everything to do with digital communications. You have computer vision toolbox. Oh no, I have it. You don't have it. Sorry, it's not with the academic license. It has to be taken separately. You get image processing toolbox. That's for image data. Okay. Then you have signal processing toolbox. That's for signals. Okay. And all these different kinds of toolboxes. So with VER, you can always check what toolboxes you have. Okay? Because each of these toolboxes support different commands. So if you don't have one toolbox, that command might run at all. Okay? A good technique of getting used to the various functions is using the help command. So MATLAB has a lot of documentation on all its functions, and it has a lot of examples and tutorials. So just type help and the function name. So if you want help on, say, ones is a function that they have. You just type help and ones, and it will give you a whole lot description on it. Okay?
How do we see the help again?
You just type help and the function name. Yeah, on which you want help.
Oh.
Otherwise, you can do it with the normal search here and just go to one, just search for ones.
Can you please show us again how to see the list with all the functions?
Oh, sure. So to see all the toolboxes, you use ver command. That's a version command.
Oh, VR.
Yeah. Okay.
Thank you.
Yep. And don't worry, I'll be giving the list of all these commands separately with the video that we upload. Okay, and all the demos as well. So you can play with them as much as you want. Okay, so that's about it for the introduction. Next, let's go to the complex numbers. Just to make you guys feel comfortable with it. Okay, so step by step. You can write a complex number directly as 1 plus 2i, 1 plus 2j in MATLAB. Okay? So this will give you the output like this, 1 plus 2i, where 1 is your real part and 2 is your imaginary part. Okay? 2 is your imaginary part, 1 is your real part. Or you can use a complex command function. It's an inbuilt function called z equals to complex. Okay, that's weird. Z equals to complex, where the first argument is your real part and your second argument is your imaginary part, the coefficients that you want to put. So this will give you the same result as above. Okay? Now, real and imaginary IMAG. Real and IMAG will give you the real and imaginary components of your complex number separately. Okay? So it will filter out the two. So Z real will be 1 and Z IMAG will be 2. Okay? And let me know if I'm going too fast or something, or if you have any questions, just stop me. So what ABS does, ABS gives you the absolute value. So let me just write it down for you. So you have a complex number z equals to 1 plus 2i, for example. It's visible. Yeah. So ABS gives you the absolute value. Okay. This does not do anything more than doing the square root. It computes this square root of the squared coefficients that you have, real and imaginary parts. Okay, so it'll give you root 5. You can do this using the formula. So there are two ways. Either you can use ABS directly, or you can use SQRT of real square, the thing that you get the real part, plus IMAG square. So either you can use a formula or the function. Okay. Going back, angle. So angle function gives you the angle. Nothing fancy about it. Here, the angle function returns you the angle in radians. So if you want it in degrees, multiply it by 180 over pi. Okay? So don't forget about that. So Q over here that you see, this is in radians. And whenever you answer your homework questions, it's better to give it in degrees. So always multiply angle with 180 over pi. Okay? And in MATLAB, pi you can write as p comma I. So pi is pi. Sorry. Okay? So you can use pi directly to use pi anywhere you want. Okay. Now, once you have the absolute value and the angle, you can reconstruct your complex number again using the polar form. So your polar form is your absolute value into e raised to power iq. Now, exp is your exponent function, which you have e raised to power in your theory. So if you look back, you have z is equals to r e raised to power j theta. This in MATLAB will be z is equals to r into exp j into theta. Okay? So exp is your exponential function. Okay?
How do we get theta in MATLAB?
Sorry?
How do we get theta in MATLAB?
Theta or q is just a variable. Theta is using the angle function.
If, like, we want to solve for something.
Solve for
I'm just asking about how to get the...
using the angle function. Using the angle function. So you have z equal to 1 plus 2j already. R is equals to abs of z. And your theta is equals to angle of z. Okay? So using the angle function, you can get theta. And then, just to be sure that you're doing it correct, when you put these values in these formulas, you'll get the same z. Okay? Cool. Okay, so coming back, I just did that. I just put in the same values that I calculated in z again, and then I displayed it, and then z is the same, 1 plus 2i. Okay? Yeah.
I just have a quick question.
Yeah.
These files, will they be uploaded to this?
Yes. You can play with them as much as you want. Yeah. Okay. Now, as we come to plotting. So, for plotting, you can every time you plot, a new figure opens. So this is like a new figure that has opened. But the next time you plot in the same program, it will overwrite this figure because it does not know which window you're talking about. So to differentiate between two different plots, you explicitly tell it to open a figure every time. So the figure command opens a new figure window. Okay? And that's the active window in which it plots. Okay? So the next plot that I have, it has another figure command. So it opens up another window. If I don't have this figure command, it will override the previous one. Okay? So just be careful. You might, if you don't use the figure command and you have multiple plots to show, then use the figure command to separate all of them. Otherwise, it will keep overwriting the same window. Okay? So plot is your basic command to plot your complex number over here. Okay? Z is your complex number, so whatever you're plotting, that comes first. Another thing that you can do is instead of Z, put real part of Z and imaginary part of Z. So this command and the previous command, the plot Z directly, they give you the same output. Okay? Because plot over here, Z already has its x and y components, the real and imaginary components in it. And here you're just applying them separately in this command. Okay? So after Z, this is the description of the marker. So when you're plotting, there are a lot of properties that you can change. The marker that you use, the size of the marker, the color of the marker even, or the lines, the line styles, everything. There are a lot of properties, and I would wish that all of you explore the properties because there are numerous properties. Even I don't know all of the properties right now. Okay? So just go and check those. So this will give you a circle sort of a marker. If you see here, the blue circle. Let me give it to a big thing.
So you put an O. Right?
Yeah, you just put an O. If you want...
If you put any letter, it will mark it like that, right?
No. not any letter, it has predefined ones. So let me show it to you. So in help, you can just open the plot command that you have. And let's just see if I can find markers. Okay, yeah, so this is markers. O gives you the circle sign, plus gives you the plus sign, you have asterisk, point, cross, square, diamond. Only these, nothing else. Okay. So pretty much a lot of options, not bad. So this is a property of the marker that you can use. X label and Y label. So it's always a good idea to label your figure so that all of us looking at your figures have a clue of what you're plotting. Okay, so don't forget to label your figure when you're turning in your plots. Okay, so if you see in this figure, my X label is real axis, imaginary axis. So whenever you're defining a string like this is a string of characters, keep it inside single quotes. Okay, always keep it inside single quotes. MATLAB will give you an error if you don't use these single quotes. Okay, so X label will assign a label to your X axis, Y label will assign a label to your Y axis. Okay, similarly you can have a title as well. So there is a title command which you can have a title and will come over the figure where I'm pointing with my arrow right now. Okay. In addition, if you don't want to use the command, which I think you should, it will give you a very good idea of what you're supposed to do. You can insert everything from here as well. Okay? So you can directly manipulate the properties from the figure window as well. So if you want to enter title, you just click on title and it starts blinking and just type anything, complex number plot. And here you have your title. So you can either do it with a command or in the window itself. Okay? Now going further, axis. So this command sets the range of your axis. So just carefully look at what I'm showing you. -5 and 5, this is the lower limit. The -5 is the lower limit. Oh God. -5 is the lower limit of x-axis and 5 is the upper limit of x-axis. Similarly, again, -5 is the lower limit of my y-axis and 5 is again the upper limit of x. So there's a pattern. Lower limit of x-axis followed by upper limit of x-axis followed by lower limit of y-axis followed by upper limit of y-axis. Okay? So let me just write it down for you. So to control the axis range, axis command, brackets and then square brackets. So this is x low, x upper, y low, y upper. Okay? Or min, max, whatever you want to call it. Okay? So by default, what MATLAB does whenever it plots it, it sets these limits according to your data. So whatever minimum, maximum your data has. But every time that does not give you a very nice plot. You want to change your axis limits to have a nice looking plot. So here it ranges from -5 to 5 and -5 to 5. Okay? Next, so if you do a simple plot with MATLAB, let me show it to you how it comes. It does not come like this the way I'm showing it to you. So if I do figure, so this is how a new figure opens whenever you type a figure. And this is the active window where it will be plotting. Okay, so if I do a plot Z and I use a star sign, can you see it? Where is it? There are 4 complex numbers. Now Z is a matrix for a very funny reason. Let me just do it another way. Let me just use the example that we are using right now, x plus 2y, and let me plot x comma star. Okay, one more thing. Whenever you're in a command window and you want to use a previous command that you've already used, you can always use the up arrow on your keyboard to display the history. So it will display the list of all the commands that you've used in the past. Okay, so these are some tricks. And yeah, so this is how your initial plot looks without any manipulation. There's no X label, there's no Y label, your ranges are not set, and your axes are on the corners. Whereas in this figure, your axes are on the center, which is better way to look at for complex numbers, since you have 4 quadrants and you can see the 4 quadrants. Whereas here you cannot. There's just one quadrant that it's displaying. So to get your axis in the center, that's what I've done. Okay, so grid on. Grid on is another function. I'll come to this later. Okay. I've named the axis of this figure as AX1. So GCA gives me the axis properties as an object, and those have been assigned to AX1. Okay, so that I can manipulate them. Okay. You can again go into help and see more details on these functions if you want, or I'll just put in the description when Now, here the x-axis location I've set to origin, y-axis location I've set to origin. So now my x-axis location and y-axis location are in the center. It's governed by the origin. Okay, which is 0, 0 in this case. So it's a good idea of how to do this. Another thing, in a lot of theory and in a lot of books, you'll see a vector pointing from the origin towards your complex number. Okay, like you can see here, this red arrow. Okay, to get similar sort of plot from MATLAB, Quiver is a function that you can use. So Quiver plots a vector from 0, 0 to where your complex number is. So 0, 0 is x, y, first xy, x1, y1 you can say, and real z is x2, imag z is y2. Okay? And again, this is again set to the same. Now, grid on, I had skipped that. Grid on does nothing but, here you can see that it's all a blank figure, blank plot. Grid on just shows these gray lines so that you can see what exactly the value is. Okay, just for debugging. Yeah.
If you close, like, when do those figures, how do you open those figure windows?
They don't open.
Like you just. Like
These?
that one, yeah. So you have them in the command window. Do they pop up right from the command window?
No. I mean, whenever you call the figure command, they'll open up as separate windows.
Oh, okay.
Okay, and they'll be on your desktop bar.
Okay.
Okay, and you just click them as the normal program that you do.
Okay.
Okay.
Like if you were to close them, can you open them again?
No.
Oh, okay.
The same thing won't open again.
Okay.
Okay. So yeah, just don't close them. Otherwise, you'll have to again run the same command. Yeah. Okay. So grid on gives you a grid on x and y axis on your plot. Hold on. Hold on is another nice command. So I had this figure. Initially, I had only plotted this point. Now I want this vector to be plotted on the same figure. Okay. For it to come on the same figure, you have to use hold on command. So what hold on does, it holds on to your previous plot that you have and inserts a new plot in the same area. Okay. So you can have multiple plots like this, like multiple sine plots with different frequencies. Okay. Yeah.
Since you had like the circle and the vector arrow, do you have to call them both AX1 equals GCA, or do you call them separately AX1 equals 2?
You can do it separately. I've just done it same over here, but it's fine.
So when you put in the same, they're all added into the.
Yeah, so here I added this later, so you don't need both of these commands in duplicate. You only need to do it once.
Okay.
Yeah. Yeah, that I'll remove. That's something I added later on, the quiver thing. Okay? So you don't need to set the properties again and again every time you plot. It's just once. Okay? And basically you can set it at the last point at the very end when you're done with the plotting. Okay? This is the same thing, it's just with a different sign. So the same, you can either supply z or real and IMAC parts separately. Okay? And this is a different figure, so I've named its axis properties differently because I don't want the two to conflict with each other. Okay? Now to get the conjugate of z, we have a conj function in MATLAB which calculates your conjugate. So let's say we have x, which is 1 plus 2y, and I want conjugate of x. What will be conjugate of x?
1 minus 2y.
Great. And there you have it. Okay. Then you have z1, you have two complex numbers. You can add them, subtract them, multiply them, divide them. That's just basic calculator arithmetic over here. Okay. Now, for your transformation from Cartesian to polar, let me show you something before we go here. So in MATLAB, the angle function that we have, this calculates your angle in radians. Okay, and it uses the arctan2 function for this. Okay, not the arctan. There's a difference between the two. Okay, so if you see arctan2, this accepts two arguments, two input arguments, y comma x. Can you see it? Yeah, sorry. Okay, y comma x. Whereas arctan only accepts one argument. That is the ratio of y over x. Okay, so one argument of y over x. Okay. So arctan would not always give you the right answer. So it's preferable for you to use arctan2 because arctan2 gives you the right answer in the right quadrant. Okay. The reason for this is, if you have two complex numbers, say 1 minus j and minus 1 plus j. Okay, and let's do a very rough plot of where these would be. So this is your imaginary part, this is your real axis, this is your origin. Where would 1 minus j be? Which quadrant? First, second, third, fourth? Fourth, right. So real part 1 minus 1, and this is your 1 minus j. Where will this minus 1 plus j be? Right. So minus 1 and j, and this is where it will be. Now, what are their angles if you look from here? Just a guess. For my 1 minus j, if you want to say, just a guess.
Minus 45.
Yeah, minus 45 degrees. And for the other one?
135?
Right. But if you see the ratio of these two, the ratio of these two is the same. The ratio of y and x, the imaginary and the real part. That's what arctan uses. Imaginary part over real part. Here the ratio is same, that is minus 1. And it will give you the same angle for both of them, which is not the case, as you can see from the figure. Okay? So arctan, you supply, so for the first, this one, arctan2, you will have, first is your y, and then is your x. Y is your imaginary, and then your real. So you have minus 1 and 1. And here, in this case, you have arctan2, oh my god, plus 1. minus 1. Okay, and these will give you different results. Minus 45 and plus 135. Okay. Now going back to MATLAB. This is what it has done. The 1 second, let me go back. Okay, so here, if you see this line, I have defined Z as a matrix of complex numbers. You can do that. That's perfectly fine in MATLAB. Okay, so Z is now a matrix of complex numbers. What would the size of Z be? 4 by 1. 4 rows, 1 column. Okay? Now, MATLAB has two functions, cart to pole and pole to cart. So cart to pole does Cartesian to polar conversion, and pole to cart does polar to Cartesian conversion. Okay? It's better if you understand the theory first so that you can verify that it's giving the right result. It is giving the right result, but so that you know that it's the right result at least. Okay? So the inputs for cart to pole are the Cartesian values that you have, the real part and the imaginary part, and it will return you the R is your absolute value and theta is your angle. Okay? Theta is again in radians. Just remember that. Theta, whatever you get, is always in radians. So you always have to multiply it with 180 over pi. Okay? Which is shown here 57.2958. Okay? Pole to cart is the same. If you want to see, I would advise all of you, before using any function, just go through its help. It will give you all its properties, what all can you do with it, what sort of inputs does it accept, what sort of outputs are expected. Okay? So for pole to cart, your inputs are theta and rho, and will give you x and y. Okay? And all of this is very graphical, so it's very easy to understand. And we are here if you have any doubts. Okay, moving from complex, any doubts? All good till now? Yeah? Okay. So moving from complex, yeah.
What's the 57.29?
That's 180 over pi. So if you just do a quick calculation, 180 over pi, that's 57.2958. Okay? Yeah, I'll add comments regarding it. Okay? Now, just to give you a brief intro of how to define signals, how you can plot them, just manipulate them in MATLAB, I'll go through a small, I hope it's a small demo. Yeah. So first we'll go to unit step. I'll first define what unit step is. You can see it, right? Yeah. So unit step function. As it's evident from the name itself, let's say this is your time axis, and this is your u of t. Okay? So your unit step function is 0 for t less than 0, and it goes to 1 at 0, and then remains at 1. Okay? So 0 for t less than 0, and 1 for t greater than equal to 0. Okay? That's a concise way to write unit step function. This 0 for this condition, 1 for this condition. Okay? Now, MATLAB has two different implementations of unit step. One is called Heaviside, and one is called step fun. Okay? Now, if you see, let me show it to you. The difference lies only in the way they handle the value at 0. So, Heaviside assigns a value of 0.5 at t equal to 0, and step fun assigns a value of 1 at t equal to 0. That's the only difference. Okay? Yeah.
Why would you ever need to do that?
Why would you need to do that? Depends on your application. One is a very continuous transition, very smooth transition from 0.5 to 1, and one is a very drastic transition. Okay, so depends on what sort of, these are like inputs to your system. So what sort of input do you want to supply to your system? A very drastic step or very smooth transition? Okay, so if your system cannot handle a very drastic transition, that's when we use Heaviside. Okay, so let's get back to the demo. Okay, so for this, I mean, in MATLAB you can't have minus infinity to infinity. Okay, so you use sort of a range of numbers. So this is how you define. X is your t over here, the t that I defined in the figure, that's x over here. It's starting from minus 100, incrementing by 1 every time, and going to plus 100. Okay? Right? Now, u is just Heaviside of x, and then I'm plotting it. Let me just run it for you. Oh, one more thing. These three commands, clear all, close all, and CLC. Clear all clears all the variables that you currently have in your workspace. It deletes all of them. Okay? Close all closes all your figures that are open. And CLC clears your command window. It does not clear any variables or close any figures. It just gives you a blank command window. Okay? So I generally have all of these right at the beginning of the script so that it's a fresh start and there's no conflict in variables at any time. Okay? So let's see what the plot is. It's a funny looking plot. Okay, again, so this is all zeros still here. Okay, here you can zoom in using a basic zoom function. If you look at t equal to 0, there's a value in between and then it goes to 1. There's no drastic change. It does not jump to 1 directly. So it goes to 0.5 and then it goes to 1. Okay, so that's Heaviside. And then it's the basic change. So title, which I had shown you to write directly from the figure, you can write it from the command as well, from your program as well. Okay, so you can control everything from here as well, whatever you can control from the figure window, and change everything. Okay, axis again changes your range. Okay, just to make it a better looking display.
Is that in green like a comment or?
Oh yeah, sorry. Everything in green is the comment. So your comments start with a percentage sign. So whenever you're writing programs, if you want to comment anything, just use a percentage sign. You can comment one line with a percentage sign. And a shortcut for comment is Control plus R. Okay? Control plus R. Okay? So to comment any line, just select that line and then press Control plus R or Command plus R if you're using Apple MacBooks. It's Windows uses Control plus R. Okay? So comments are useful whenever for your own use. You have the idea what the program does. Each step you can comment, this is the step. So it's a good idea to add comments to your programs. Now the second plot, this is your step 1. Let me make it bigger. Here you can see it's 0 right before t equal to 0 and then directly jumps to 1. Okay? Does not go through 0.5 or anything. Okay? So these are two different things, two different ways. Sorry? Oh, sorry. I'm so sorry. Oh God. Split screen. Okay, so step 1, just to repeat, it goes to 1 directly at t equal to 0. There's no transition at 0.5. Okay? There's a direct jump from 0 to 1. So it's a more drastic jump than Heaviside. You can see it's a more drastic slope, vertical slope. Okay. Next is time shift. So you can shift these signals left or right. By left, so if you shift a signal to left, what's it doing? Advancing or delaying? If I shift it to left in this figure, yes, that's advancing or delaying.
You're to the left, then you are advancing.
Yes, that's correct. Because your transition is coming before t equal to 0. Now it's coming at, if it's t plus 1, it's coming at minus 1 right now. Okay? If you shift it to right, it's delaying. Okay? So for delaying, it will be t minus 1. For advancing, it will be t plus 1. So let me write that for you. Time shift. The same signal as above. If I do it over here, this is minus 1. U of t plus 1, and this is t. That's visible, right? Yeah. And this is 1, and this is u of t minus 1. Okay? So this is advancing, and this is delaying. All good? Okay. Come back to the demo. That's your time shift. Let's see it over here. So what I've done is x minus shift. Shift is a variable that I've defined. Shift. Shift is 5. It shifts by 5 units. Okay. So if you compare this one with the previous one, let me zoom in for easy comparison. It's not that easy, but yeah. If you look at t equal to 0, the function is shifted to the right now. Okay, so shifted by 5. So now your transition is occurring at t equal to 5, not t equal to 0. Okay, so that's basic shift. You can shift left or right. Next is scaling. So you can scale as well. What are you're scaling the output? So instead of outputting 0 and 1 right now, it will output 0 to 0 and 0 for t equal to t less than 0 and 2 for t greater than 0, or 5 or 10 or something. You can scale it. It's like amplification. You're amplifying your signal. Or you can decay it as well, half. Okay, depends on the scale that you choose. Okay, so scale over here is 2. If we go over here, wrong figure. It should be scaled. Why isn't it scaled? It is scaled. Okay, so this is not that's amplitude scaling that I just told you. There are 2 scalings that you can do: amplitude scaling or time scaling. Okay, so amplitude scaling, you have the same amount of the signal for the same amount of time. It's just double in amplitude. Okay, if you're doing time scaling, then the signal spreads or comes closer. So let me just write it down. So if you have scaling, there are 2 things. You can either scale the amplitude or you scale the time axis. Okay, so if you're scaling the amplitude, this thing now goes to 2 instead of 1. Okay, u of t. If you're scaling the time axis, let me show it to you with a different thing. So your normal, if you're using rectangular pulse, so your normal rectangular pulse, say for duration -1 to 1. Okay, so if you're doing time scaling, it will either double, so it will go from -2 to 2, or you can reduce the time scale as well, and it will go from -half to half. Okay, that's what time scale is. So here I have scaled x, and then that's the scaled version that I'm supplying to step 1. Okay. If I'm doing amplitude scaling, I will multiply. Oh, sorry. Okay. Again. So scale x is being scaled. That's your time axis being scaled right now. Okay. And that is being supplied to your step 1 function. If I'm doing amplitude scaling, I'll multiply step 1 over here externally. Okay. Great. Any questions anywhere? No. Now, exponential functions. So you have 2 types of exponential. One is increasing, one is decreasing. So increasing is your positive powers and decreasing is your negative powers. Okay. So again, my time axis from -1 to 1 incremented by 0.1. So it increments by 0.1. Starts at -1, ends at 1, and increments by 0.1. Okay. This is the same thing that is used in your for loops as well in MATLAB. This is the same way to construct your for loops or while loops. Okay. You want to do. So exp, as we had used before, gives me the exponential function. Okay. And I'm just simply plotting it.
Can you explain the t again?
Sorry?
The t -1.
Okay. So t starts from -1, ends at 1, and is incremented by 0.1. Okay. So the first thing that you specify is the starting point, colon the increment amount, colon the end point. Okay. So this is your positive powers. Let's see what it looks like. So this is your exponential function increasing. Okay. Let me just show it smaller. It looks better. Now for decreasing power, I'm just supplying -d. Okay. For decreasing exponential function. And that will look like this. So increasing, decreasing. Okay. And exp is a simple command to plot exponential functions. Right. You can write e raised to power t actually the way you write. So you can use these power operators and it will actually give you, if you notice over here, e raised to power t. It will not show that power symbol and it will give you correct label. So do use your labels carefully. Okay. Now rectangular and triangular pulses. That's they're standard signal processing signals that we refer to all throughout the course. So again, here my t is ranging from -5 to 5. So you can change it. It can go from -100 to 100, increment by 1, -1 to 1, increment by 0.1. Here it's ranging from -5 to 5, increment by 0.1. Okay? So it's completely your choice, whatever range you want to choose, or whatever is specified in your questions or assignments. Okay? So for rectangular pulse, there's already an inbuilt function called rect pulse in MATLAB that generates your rectangular pulse. Okay? And here you can also control the width. So if you quickly go to rect pulse, and that's why I'm telling you to refer the help. That will describe all the additional properties. So your rect pulse can be defined like this or with t comma w. Okay? So with w you're controlling your width. And it gives you all the examples. So it's pretty easy to understand. Okay, so let's see the rect pulse. This is the rect pulse that we have. Okay. Ranging from -5 to 5, it's 0. And it's, so by default it's unit width. Okay. And so 0.5 over here, 0.5 over here. 0.5 to the left of 0, 0.5 to the right of 0. Okay. And by default it's unit height also. So you can change the width and height as well. Height is just a multiplication by whatever amplification you want to supply. Okay. Okay. And then again, your rect pulse can be shifted like we had shifted the unit function. So this is original and this is shifted. The shift was t plus 1, so now it will be centered at t equal to -1. By default it is centered at t equal to 0, which is your origin. Once you shifted t plus 1, it will shift to left. If it's t minus 1, it will shift to right and be centered at t equal to 1 in case of right shift. Okay? And shifting is nothing. I'm just applying t plus 1 over here. Okay? And you can, instead of 1, you can use a variable and then set the variable to 1, 3, 5, whatever you want to do. Okay? Instead of just hard coding it. And what else? Triangular pulse. So, with tripulse, you can control 3 things. T is your time axis, W is your width, and S is your skew factor. So, if you go to tripulse, so you can define simply T comma W, and D comma A, W comma S. All of these have some default values. Okay? So, by default, W is 1, okay, and by default your skew factor, skew is like if your triangle is centered or is it leaning towards one side or not, that's skew. Okay, so I'll just show it to you, the skew factor as well. So by default it is 0, that means it's symmetric. Okay, so here if the skew factor is 0.5, so this is my triangle pulse. It's centered at 0 but has a skew. So if it's positive, it will skew to the right. If it's negative, it will skew to the left. Okay? So that's just a point of asymmetry that you can add. And it's tripulse, again, you're supplying T, the width, and everything. Now shifted. So T minus 1 will shift where? Right. And it will be centered at? Where it will be centered? Sorry? Yes, T equal to 1. If you're shifting it to right by 1, it will be centered at 1. It's initially centered at 0. T minus 1 will center at 1. T plus 1 will center at minus 1. Okay?
What is the 2 and 0.5? The argument?
2 is the width and 0.5 is the skew factor.
Oh, the pulse.
Yeah, of the tripulse. So it's controlling the shape basically. So here the width is 2. By default it would have been 1. So it would have gone from minus 0.5 to 0.5. Now the width is 2, so it's going from minus 1 to 1. Okay? And if the skew would have been 0, this would have been a normal triangle pulse that you see. Okay? But the skew factor is 0.5, so it's shifted, it's leaning towards right. Okay? Now if you see the shifted, where is it? Yeah. So it's shifted to right by 1. Centered at 0, shifted. Okay? Makes sense? Now, you can reverse your pulses as well, your signals. Okay? So what does reversing do? Just to give a quick example. If you have your unit step, and your unit step goes like this, what do you think reversing would do? Flip it, right? So now your unit step will be like this. And this is written as u of minus t. Okay? If you flip a rectangular pulse, you won't see any difference. If it's centered at 0. If it's not centered at 0, then you'll see a difference. Okay? So similarly, that's what I've done here. I flipped a triangular pulse over here. So for flipping, I'm just applying it with minus t instead of t. Okay? And here we go. So this is original, and this is the flipped version. Okay? It flips about its center. So it's centered at 0, it flips about 0. Okay? Now, impulse function, your delta functions. Here t ranges from minus 1 to 1 with increments of 0.1. Okay? Here. Okay? Now, to define an impulse, I've just defined it logically. Where is the impulse? Impulse is at 0. So, impulse is 1 whenever t is equals to 0. So what this double equal to sign does, it's comparing the value of t with 0. Okay, so impulse will be 0, the variable impulse over here will be 0 whenever t is not equal to 0, it will be 1 when t is equals to 1, and then again it will be 0 when t is not equal to 0. Okay, so then just plotting it, this is what your impulse looks like. So plot is doing a continuous plot, so it's all 0 here. At t equal to 0, it's suddenly 1, so this is interpolating values. These are actually not in your data. It's just connecting these 2 points. Okay?
Can you go over the...
Sure.
Is that like an if statement or something?
Sort of. It's more of a logical statement. So it's comparing t with 0 for all these values. Okay? So it's at only one instance t will be 0, right? Everywhere else t will not be equal to 0. So whenever t is not equals to 0, impulse variable will be assigned a value of 0. As soon as t becomes equal to 0 over here, that means this becomes true. Everywhere else this condition is false. So as soon as this condition becomes true, impulse becomes 1. Okay? Fine? Right?
Be like
Yeah.
a spike, right? 'Cause it's only the true
Yeah,
value.
yeah. It's actually a spike, but it's interpolating over here.
Oh, okay.
Right? So it has the plot function has 1 point over here and 1 point over here. It has to connect those points to the line. Okay? To show the spike, the idea of spike that we have in our mind, I've just done a different kind of a plot, which is a stem plot. This plots values at discrete instances. So it will not plot at 0.5 or 0.6. It will plot at 0, 1, 2, 3, 4, all the integer values, you can say. Okay? So let me show it to you. This is what a stem plot gives me. You have a spike at t equal to 0 and everything else is 0. Okay? So this is in accordance to the idea of impulse function that we have. Okay? And yeah, now sine and cosine are basic trigonometric functions. So here your input is theta, the angle. Okay? Just like the way you had made a range of values for t, the time axis, you can make a range of values for theta as well. Okay? So you're starting from minus 2 pi, incrementing by pi over 4 every time, and going up to 2 pi. Okay? And this MATLAB has inbuilt sine and cosine functions. Okay? Don't forget, these are radians, these are in radians, so always use radian values for your input theta. Okay, and you can convert any point of time. It's an easy multiplication. Okay, so just a simple plot. And another thing that I'll show with this idea, you can have 2 plots in the same figure. It's not necessary to have 1 plot every time. Okay, so here you have your sine function going on, cos function. Okay, how do you get 2 plots or multiple? You can have more than 2 plots as well. Okay, so what we do here, we use the subplot command. Subplot command divides your figure window into sections. Okay, so here 1, 2 means vertically divided into one section, vertically meaning in this direction, up and down, and horizontally along the screen divided into 2 sections. Okay, this one, the third parameter, it defines to the section that you're plotting in, like the first section or the second section. So here you see 1, 2 is same, 1 and 2 are different. So the third parameter changes. Okay. So this divides vertically in one section. So there is only one section vertically, and horizontally there are 2 sections. Okay. Yeah. So that's it for the first session. And I'll still be here around till 2:30 or so, so we can start with the office hours. Okay, thank you. Andrew, that's it. Thank you.
Thanks.